How we doing, Josh?
Well, how are you doing?
Another wonderful day.
Pretty nice out.
I actually might just get to do that. I was like, it's a great day. So we were in the midst. This is calculus 4.
Oh, wow. See, that's more than you can.
I don't know about that.
Yes.
All right, so when we were talking about using the undetermined coefficients method to find equations, and I wanna adjust this one to make it a little bit more interesting. So with the sums, we make all the individual equations, all right, and then all right, see if we can line it up with what the g of t function is. So for this guy, our g of t, -2 sine t. Okay. All right, so when we guess our particular function, everything we look at is going to be about, all right, making sure the angles. So, all right, we see two different angles here, which means that I have two different guesses that I have to combine. This guy, all right, that's one guess. When you have a sine, just the sine alone, what's our guess?
Cosine and sine.
Cosine and sine. So, and then we just match the angle. So I'm going to do A cosine of 1t plus B sine of 1t. All right. And then those, and this is actually repeating itself, right? Because this is 14t, 14 theta, all right? And since they're the same, actually you have both pieces. So I can just keep adding on. C cosine 14t plus D sine of 14t. There's no additional polynomial or exponents mixed in here. All right, so our guess can just be straightforward. We have sines and cosines. You guys okay with the guess? Because this is where all the thought's going to come in. For the next one, g of t, e to the 7t plus 6. All right, so for this one, the main piece here is we have an exponential. So a e to the 7t. And then the big part here is, what is this?
Not a polynomial.
That's a polynomial, right? Technically.
So I have like t squared or t cubed or just 6t? Like what is the guess going to be?
Ah, that's a good question. Polynomial, what degree is this polynomial?
7t is 0.
0, which means.
Does it solve?
But that is an important part that we understand. That's polynomial, just happens to be degree 0. I was like, which technically violates the definition of polynomial, right? Polynomial. But that's the idea, all right? Non-negative, actually non-negative integer. So yes, 6 is a polynomial, just degree 0. Okay, so this one I changed. I was looking at these and I wanted to make this more interesting. All right, so for a particular guess, basically we just have a bunch of exponents. So without a doubt, all right, first and the last one are the simpler versions. All right, and it's just kind of like looking at what the exponent is to make sure it's all included there. So a e to the t, and while I'm at it, I'm just going to take the last one too, plus b e to the 6t. Those are individual polynomials, got them both accounted for. For the middle one, what's going on?
Polynomial and exponent.
Polynomial and an exponent. All right, so can I just do that with plus c t e to the negative 8t?
No.
No, what am I missing?
Yeah, degree of t,
Degree of what?
1,
1. Degree of 1, which means I have to account for,
constant.
yeah. So I actually have to go all the way down here. So ct plus d e to the negative 8t. And that's right, when it's being multiplied, make sure you have all the pieces. And that's it. I was like, I wanted to change it because if you noticed what it was, it already had e to the negative 8t. So sometimes people just accidentally put that in and it would be correct accidentally. I want to make sure that we constantly remember, all right, we have to account for all powers down to 0 of the polynomial. Okay, so with this guy, what are we looking at?
Two polynomials. Cosine and sine.
Cosine and sine, but remember, so
Sorry,
go ahead.
the coefficients, we gotta remember to add.
Absolutely. But if I have t and t squared, which one actually matters?
T squared.
T squared. Also look at the angles. Since the angles are the same, all right, that means I actually just have,
Already in that form.
yes, I already have one bigger polynomial. Look at the higher degree, all right, and then we're going to count it down. And since I have the same angle, my particular guess, and this is the one I love speeding up, because since I have a t squared plus bt plus c cosine of t plus dt squared plus et plus f sine of t. The higher degree has to be accounted for, because technically I wrote this out. This is written out just for this one. This part is actually repetitive of what I already have, just writing this one out completely. All right? That's already accounted for because I got ET. And here's the big thing we're going to get to today as well. You have to have a distinct constant for each basically function that is created, right? Because technically I have the function t squared cosine t that has constant a. I have the function t cosine t that has constant b, right? And that's the big thing. So the constant is distinct for each distinct function, right? Because I don't want to write this repetitively as we're about to see. I'm going to throw it right here. Because what we're gonna start seeing, and this is where it becomes really interesting, is complementary and particular solution overlaps. Everything we do, we need distinct equations, and we already saw this actually when we were solving in our chapter 3 stuff with, we need distinct functions, right? We had to multiply when we had a double root, we had to multiply the function by e to the t, okay, in order to create two solutions. We're gonna have to do that along the same lines here. So in those cases that we just looked at, we were just looking at the g of t function, all right? And then, all right, now we need to look at the complementary solution in addition to the g of t function that that's created. So back to, this is the same one we've been looking at, second derivative of negative 4y prime minus 12y. We've seen our complementary solution here multiple times, which is c1 e to the negative 2t plus c2 e to the 6t. Now, all right, we want to guess. So if g of t is e to the 6t, we want to guess our particular function. And what would our guess be?
AE is 16.
AE to the 6t. 100%. Let's go through the process of solving this. 100% with the guess and everything. Double prime, or prime, double prime. Then plug in the YPs into the DE. What do we see on the left side of the equation?
Cancels out.
Yeah, 0. That can't be true.
Aha, right? By definition, right? We know that there's an asymptote for the exponential. All right, this is then a contradiction. Right, ever true. Which means, all right, it seems like we had a bad guess for y, p, and t. All right, for our particular solution. Looking at our guess for the particular function and looking at the complementary, do you see anything?
There's no negative 2t.
I mean, yes, but
C2 and YT are the same.
no, A and C2 are the same. This function,
Pairs with that.
yes, and this is what I was talking about. Each function needs a distinct constant to go with it. Is this constant distinct? By definition, no. I was like, they'd be exactly the same. Because if I solve for this constant, all right, and this one, I would get the same value, which means this is why I ended up with a contradiction, because I can't have multiple, I can't be solving for multiple constants that represent different things. Which means that the solution is the same solution that we did for the double root, all right, in order to improve this guess. I would start with the same thing, then I would say, oh my God, it just looks like my constant. Multiply it by a t. And I end up with a t e to the 6t. We can then be aware, I can then go through and I could solve, right, y prime of t, y double prime of t. And I would actually end up getting a equals 1/8. The idea is that your constant needs to be solvable. And we're going to get to the point where we don't want to solve, we don't want to do this. Okay, we don't want to go through and solve for the constants every time. So we just have to, you have to recognize, you have to look at your equation and verify that each constant goes with a distinct function, right? Distinct constant, distinct function. Now, do I have to call these C1, C2? No, I'm starting with A's over here, right? That's the whole idea. Okay, it's just any constant, but each constant has to be next to a distinct function. Because the whole idea is I need to be able to solve an IVP all the way down. We're gonna stop solving for these constants, which means that we need to make sure that each of our constants is distinct. If hypothetically I would solve for it, because the algebra is going to start to get more and more annoying. All right, let's look at this, start creating some equations. Notice that now I have the entire second order non-homogeneous differential equation, because both parts, the complementary and the particular solution, have a relationship. All right, so for a character, always start with the characteristic equation.
Oh, it's not more.
Let's give me this.
So we start with the homogeneous, all right, characteristic equation as well. And then this should be easy to solve. R plus 7, right? R minus 4. Simple factor. R equals -7. And 4. Which means I can make my complementary solution. Right, and you guys working on the chapter 3 homework?
Yeah.
This should be take, right? I was like, we're just crushing this now. Okay, then G of T. All right, so given our G of T, now we want to start guessing the particular. So what do we see here? Polynomial and an exponential. Doesn't really matter which one you start with. Since I like the exponential, let's go with start with the exponential. A e to the -7t plus
B T squared plus C T T.
et squared.
No, it's because it'll only be one.
Ah, yeah. Don't need to go higher than
That's
whatever
necessary.
the degree is.
T plus C.
BT plus C. Now, here's where the new part comes in. Now I need to look. You look at your complementary and you look at your particular guess, okay? And then we see if we need to improve the guess. Are all constants distinct? No, clearly not. Right here, e to the negative 7t, e to the negative 7t. I cannot have two constants representing the same function. So how do I improve my guess?
Multiply it by t.
Yeah, and it's simply just multiply by t. And it's pretty much that every time, just based on if we have to improve the power. Okay, and so I'm right here. All right, now what do we need to do?
Solve for your constant.
We have to solve for the constants. But if you noticed, here is the change, okay? Because these are gonna start getting bigger and bigger. I say do not solve for the coefficients at all right? Because I just want us to think and make the correct equations. Because the bigger these are, we solve. In order to solve this, how many equations do we need to solve?
Well,
So it would be two.
Okay,
I was like, there's three pieces, but we would solve the polynomial as one piece.
I see you.
I would solve the polynomial as one piece, and then this is one piece. Individually equal to this differential equation, all right? And then remember, we put it together as we saw in the last one, right? We solved three different equations to create that one big one. So, all right, pay attention for the directions and say do not find the coefficients, which means we want to think and make sure we're creating the correct equations. And it's all about verifying against the complementary solution, all right, and making a good particular guess. And the biggest issue I see, without a doubt, that always comes with these, it's always like when polynomials and e's and sines are all combined, this is where we have to do our most thinking to make sure that this takes care of everything. And then don't add on another every time. If you need, multiply this out. Because again, t squared cosine t. T cosine t. Each function is distinct. Each constant with that function is also distinct. Okay, let's do a couple more of these. Practice these. All right, so start with our associated homogeneous function. Create the characteristic equation. Once again, easily factorable. All right, equals -4. And then these, actually, I think we're looking at all three cases, right? A, B, and C. We have all three cases of the possible variations of the quadratic, right? So when I have, right, R equals -4, this is the double root case. My complementary equation, I'll start that out. We get a bit of this now.
E to the -14.
E to the -4t.
I don't remember. Is it plus 14?
Right? Because this one is the double root. This is the one that you need a distinct function, all right, to make sure, all right, that you have a distinct constant with a distinct function. So, all right, again, there's only 4 cases. The 2 distinct roots case, all right, which is what we had here, the double root case, and then what's the other way to solve a quadratic? What kind of numbers do you get?
Imaginary.
Yeah, imaginary numbers. So there's only 3 cases when you solve a quadratic, right? Okay, now ready for the g of t equals t. So when doing the particular guess, always just base it on that function to start. So what are we looking at here?
None of the constants are gonna work out right because of all the differences.
Go ahead.
You have to multiply everything by t again.
Okay, well, let's make our guess first. I have a feeling, yes, that's what we're gonna do. I was like, let's start with the guess.
You can do AE and negative 4t.
And then we have a polynomial, so you gotta break that to like bt squared ct plus d. So and then as we multiply by the e to the negative 4t, we won't have a particular solution per one because the a's don't match up. And then
Okay, all right, you're jumping ahead, sorry. You're absolutely correct. All right, well, let's just look at this, because this is where I want to start with my guess. I was writing out exactly what we had down. Just with this guess, do I have all functions distinct? No. What's going on?
the constants aren't matching up.
Specifically?
No, it's
One
just
and A.
Huh?
C1 and A.
Okay, nothing to do with C1 at the moment. Are all these constants?
Oh, no. A and
No, A.
Ah,
But then-
careful when you do this.
in their own.
Yeah, look, just look at this. D e to the 4t, A e to the 4t. This got double counted, which means all we have to do is just cut that away. And that's, so what can help there is always, if I just every time multiply it out, I always leave it like this and then just look. But double check.
One constant, one species.
One constant, one function. What did you say?
Species.
Same difference. Yes, absolutely. Right? These are exactly the same. Okay, I have a function and two constants, which means before I even go looking at the complementary solution, which 100% we need to do, I need to improve my guess. Technically, writing it either way is correct. Okay, so I can write it as completely multiplied out or factored out. So now you guys are absolutely correct. All right. Now where's the overlap?
C1 and C and B.
And B, C2 times T, that's not,
I see actually a lot of issues. All right. So this one, maybe this one, let's multiply it out just so we can 100% see this all the way. And I'm going to write it next to each other so we can really compare. Okay, so yes, I was like, oh man, B and C2, right? C and C1. So, right, we talked about it. If I multiply this guy, so I need to multiply this one by a T, right? To change that one and multiply this one by a T.
then we get the same thing again. They're matching again.
I matched it again. So what do we really need to multiply? Because now this becomes CT. Oh, that one matches that. This one's BT squared. Oh, which matches that. So one last one. Basically,
T squared.
we can do this a lot faster if we multiply, we have to raise the power of the entire piece. If I raise it all by t squared, everything should be distinct. Because I have t to the 0, t to the first, and then the lowest power of t in the particular function will be t squared. Everything has to increase because otherwise you just keep double counting it all. And you could go through and figure that out. But the other thing is, if you have it all multiplied out at the end, you just want to give it the once over and look, make sure everything is distinct. Because again, we're not going to be solving for our coefficients here, because if you solve for your coefficients, you would end up with a contradiction if you have that particular guess. And so that's the thought. We want to focus on the thought, because I think the rest of it is just algebra. Algebra we definitely could do. And whether you multiply it out or leave it in some variation of factor form, that's completely up to you. As long as you understand, right? All constants, all distinct, no repeat functions. All right. Once again, start with our characteristic equation. Of the homogeneous associated function. And this guy would be the quad form out. Does not factor. It would then result in our imaginary roots. Dana has a saying that she loves to say. So she doesn't like to call them complex roots because real numbers, are they complex? Technically, yes. It's just 0i, right? All numbers. I find it very technical. Like, that's what I call a complex number. I was like, but she is technically correct.
I don't even want, that's some philosophical stuff that I don't even want.
I was like, that's the math proof. All right, so this ends up with our other situation where we used Euler, right? We used Euler's formula in order to prove that an imaginary can break into a function of e's and sines and cosines. And again, this is what the main focus of chapter 3 should be: repeatedly practicing these particular functions over and over and over again. All right, so we got our complementary solution. Again, solving a quadratic, and then it is always going to be one of three cases. All right, our g of t function then looks like this guy. And you can see it from here, right? Do you see some overlap?
The sines and cosines and e to the -2, the whole thing.
Yes, there's definitely some overlap between our complementary, but let's make our particular guess and then we'll compare to that. So always break this into, don't try and do that step until you have a good refined particular guess. But I mean, I could see where we're going already. Okay, so what do we need?
Polynomial, an exponential, and a sine cosine.
Are they all together?
Two of them are one part of it, and two are another.
Ah, very good. Okay. Don't blend the polynomial, the exponential, and the sines and cosines all into one giant thing. This one is an exponential. This one is a polynomial. Even though the angles are the same, it's still actually two different methods to deal with. Okay. So e to the -2t, and then I'm going to go a sine of t all over 2 plus b. Sine of t over 2. And that's just the first piece. All right, so I got that one. Now I want to do the polynomial part. With a polynomial, right? What degree is the polynomial? 1, which means I need two pieces. Yes, I need the t and the constant. This then becomes, okay, what are we on? C t plus d cosine t all over 2 plus e t plus f sine t over 2. So I have my polynomial sine cosine, and that's the nice thing. So I have sine and cosine there, right? But each of those is its own function, and each time you have to bring in sine and cosine. Those angles could be the same or they could be different. I made them the same here to attempt to trick you, right? So don't get tricked. Two different functions we're dealing with. Okay, I think that's a pretty good particular guess. Do all functions look distinct? No?
Your first one, if you multiply b to e to -2 sine t over 2.
Yes, when I multiply it out, what happens?
You have e to -2 sine t over 2, which is same as your C1.
Which is same as our complementary. Okay, before we move to complementary, are these distinct? Like last time we had some overlaps, right? Is everything here distinct?
Seems like it is.
Yes. Okay. I just mean, you're absolutely correct. We need to move to that. This step of making sure this is okay before you get to that is a big step, because we saw it on the last time, right? We had a double counted where
The A and D.
A and D, right? I was like, before you go and verify that, that's absolutely the next step, and don't forget that, like, several pieces. Okay, now we're absolutely there. So looking at, and I can see it, right? You're 100% agree. I can multiply that out, and I see that that will match exactly both of those. So what do we need to do?
By t.
Just one t, and that will solve the whole problem. And it's always that. The last one we saw where watch out for all that build. But usually it's just a single t. So I'm going to multiply this guy by t as well, right? And that will create a distinct particular function separate from my complementary equation. And that's my whole general solution. All right, so let's write that whole guy. to do with that sign first. All right, I wrote this one fully multiplied out for the simple reason that this check, now, as long as you're sure, I leave them factored and everything because it's way cleaner, right? Does every constant have a distinct function with it? But this is how you, at the end, this is what you want to make sure you look at. Are all constants and functions distinct?
Seems like a yes.
Yeah, okay. If you multiply it out and all of a sudden I have a t sine t over 2 and another one up here or another one down here, that means I messed up. But when you multiply it all out, every function should be distinct, every constant should be distinct. Okay. I love this because this is all thought and no algebra, basically. All right. So, all right, this definitely is something that you're gonna see in the home fun and we're gonna focus on as well. All right. So, undetermined coefficients method, that is without a doubt the most common because it deals with polynomials, sines, cosines, and exponentials. And multiplications and combinations of that. That covers a pretty big portion of all functions. It does not cover everything though. So, the other method, all right, is what's known as variation of parameters. Variation of parameters, all right, has the advantage that it can solve anything as long as you can do an integral of it. All right, if you can't take the integral, that's where this method becomes a little bit more tricky. The other thing is that the algebra with those, right, we even stop solving for the coefficients because the algebra just gets so long. All right, this method actually is a lot quicker as long as you're actually able to perform the integration. But this solves for all the missing ones. So I have the proof that you can browse through on your own time. The biggest part is, again, I'm all about what we're going to use. All right. In order to actually use this method, notice that it says the particular guess is. All right. You identify y1 and y2 from your complementary solution. G of t, that's the function that is the non-homogeneous part. And then what's the W mean?
Wronskian.
The Wronskian. All right. So then we calculate the Wronskian. Actually, this turns out to be a pretty clean method. As with everything, make sure you're in the proper form. The form is pretty general. Once again, just make sure you have a coefficient of 1 in front of the second derivative. All right. But otherwise, I was like, this then finds the exact particular. Now, here's the real advantage of variation of parameters. Notice what's not here, which was in the, by definition, undetermined coefficients method.
Your particular?
The whole thing is particular.
Yeah.
What's not here?
Derivatives or y prime stuff like that. Like you're asking, like.
We found our solution here. In the particular solution.
No constants.
Yeah, that actually solves for the constants, all right, through that integration. And that's actually, that's the nicest part. And it's
Is that what Wronskian does too?
No, well, through the integration.
Okay.
The constants are actually solved, all right, through this function because, you're canceling and, it's just, So that's the real nice thing. But the problem is with everything, the higher order of math you do, the more likely it is, we have to use numerical techniques or techniques of integration. So that's the downside if this is a pain. But there's a lot of other. All right, and to that end, right, the constants. Oh, look, I end up with all these constants, right, as you integrate it out. But, all right, in almost every case, all right, because the constants will just, I was like, we solve for them through the integration. We don't have to worry about them. And then I have another note. Don't worry about which is y1, which is y2 again. We said from the beginning that never matters. I was like, it balances out within the integration. All right, so let's look at an example. So I have a second order differential equation. And over here, what function for my g of t is this?
Sine or cosine?
Yeah, sine or cosine. So can I just use that equivalency that we had for undetermined coefficients?
No.
No, it has to be sine or cosine, which means this is not sine, cosine, exponential, or polynomial, which means we cannot perform undetermined coefficients on this method, right? This method, we have to use variation parameters. I point that out because does it say which technique to use? Good news. How many do we have? Two techniques. Undetermined coefficients, variation of parameter. Go ahead.
Why can't you do sine, like, a sine plus whatever cosine divided by cosine sine?
Because cosine divided by sine is
Maybe
what?
one, or cosine maybe cotangent.
Yeah. I was like, cotangent plus tangent. I can't create a function that
Does anything.
this.
Okay.
Yeah. That like a sum of sines and cosines, because remember we said every time we have a sine, we get sine and cosine. Every time you have a cosine, you get sine and cosine, which means that those ratios don't work. You turn it into sine
Into a
and
ratio.
cosine. What?
Because that tangent is like a ratio, right?
Yes, it is a ratio, but it's not a ratio that we can use to like guess.
Okay.
Which means that we have to use variation of parameters here. But as always, we still start with our same solve the characteristic equation. And the form here is important as well. Actually, the form we can fix it and solve. It'll be the same. And you divide this whole thing by 2. Everything is about form with this one, but the form is simply just coefficient of 1. All right, now I have that. I can solve my characteristic equation. And get the complementary solution. Okay, so what you pick for y1 and y2 does not actually matter. Oh, darn it. Square root of 99, which actually was plus or minus 3i, which actually means a complementary solution. Okay, so we need the Wronskian, and then basically the most of that is putting into the formula and simplifying it down and doing some integration. But we need the Wronskian, and I'm picking y1 as sine of 3t, and y2 as cosine of 3t. because the Wronskian is, right, y1, y1 prime, y2, y2 prime, and again, if you had those reversed, it'd come out the same. -3 sine squared, and once again, what do we say?
About -3. Sine squared is no sine squared.
Yep. The fundamental theorem of trigonometry. So that becomes 1. So the Wronskian is -3. Oh, well, that's already good news because, all right. Now, for our particular, and the big thing here, make sure that you have, all right, everything written out correctly, because this is just about plugging in and then making sure we simplify properly. Okay, so y1, what's my sign? So, all right, variation parameters is actually pretty nice because it is pretty plug and chug. Then it's just simplify down until you can figure out what you're doing. So if I have cosine times tangent, right, and 3 and 3, those are going to cancel on both of them.
Cosines cancel.
Sine.
Because exactly what you just said, tangent is just sine over cosine, right? So we just want to make sure we simplify it to get it to something that we can actually integrate. It's all going to be the algebra. Otherwise, this isn't very tricky. Hold it. So negative comes out, this becomes positive once again. This becomes sine over cosine, cosines cancel, which just becomes sine of 3t dt plus, this one's just to a minus cosine t integral. All right, what about this guy?
Sine squared over cosine. Then we can use, figure out what the deduction is. It's like 1 plus cosine divided by something. The sine square breaks into, and then you can do more of that, right? Cancel out more.
I was like, do we want to do that?
I don't know.
Are you talking about the half angle?
Yeah,
Okay.
there is some kind of identity to break that up more, but
I was like, so there's multiple things I want to think about. Let's see. Okay, so sine squared, if I have that, definitely without a doubt, when I have a sine squared and a cosine, what do we typically like to do?
U sub.
Okay, I would like to do u sub, but if so, what would I use as u?
You have to use sine square.
I'd have to use sine,
Or sine.
just sine. Derivative of sine is cosine, oh good. But where is the cosine?
Divided by
On the bottom.
du.
Yeah, you can't have your use of in the bottom there. So that's absolutely, always, that's first. Second is integration by parts. Neither of those are gonna work here. So now I need to actually go back to trig, okay? So if I have sines and cosines, do I want two different functions?
No,
How about one function? In order to do that, what can I do?
relate them to each other.
Yes, how can I turn sine into cosine or cosine into sine, vice versa? We just talked about it.
Oh, the primary identity, that
Yeah,
sine squared
the
is one
fundamental
minus
identity.
cosine squared.
Typically, the better approach. Okay, so we need to take a pause. The rest of this is gonna be easy, right? Tangent, different type of tangent. So this becomes 1 minus cosine squared 3t all over cosine 3t dt, which actually becomes two separate integrals, 1 over cosine 3t minus integral of cosine squared all over cosine just becomes
Cosine.
oh, look. And so yeah, don't overcomplicate it. And so this guy then, integral of secant 3t dt minus integral of cosine 3t dt. Right? The integral of secant, which I could write as 1 over sine, which we can do. We can do this out. It becomes ln, right? ln of secant. Okay, we could run that. I can run through this as ln. I can work that one out. ln of secant tangent. That's right. But the idea is, all right, is that just work through the process. Yes, you have double angles, heavy trigs. We could simplify that down. This is one secant tangent. Yes, it is ln secant tangent. Right? But that's the whole idea. All right. The only difficulty of variation of parameters is just make sure that occasionally you're going to run into weird trig stuff and are more difficult integrations. All right. So make sure that you're thinking through that part, because while it's like, oh, it seems like, and be aware, any of those problems we did above, you can do it with this, but there is no stopping once you start the integral. We can't get to a point, okay, and be like, oh yeah, that'll work. Okay, so back to the other ones, and again, the rest of that multiply by some sines, cosines stuff. So back to the particular, so that first one, negative 1/3 sine t cosine 3t minus, and that would be cosine of 3t times this whole thing that we just have right here. And we could simplify that down a little bit. And actually, a lot of stuff simplifies and cancels. Because yeah, I can already see, yeah. I have the 1/3 sine cosine right here. When I put this in, I have a 1/3 sine cosine right there. Those two will cancel, which means only the other piece is left. And what, again, so the general solution, which once again, notice no constants. It solved for, right, the constant, right? And notice that this wasn't even a nice, looking at this, there's no way we could have algebraically gotten to this with undetermined coefficients method, right? There is no combo that creates that thing. But the idea is that this is a nice method, and I mean, it gets it down so you have the constant solve, all right? And we could create an IPP and do the last piece, but. So, it is a nice method. Let's look. Let's look. All right, so start with our characteristic equation of force. And this is already in the correct form. Again, the only part of the form is that the coefficient of the second derivative is 1. This guy is r minus 1. And so this is a double root. Which gives some complementary equations. Make sure it's 1, 2. So the double root one, right? Function, and then the function multiplied by t. You only get one solution. And I'm picking y1 as e to the t, and y2 as t e to the t. Find the Wronskian. So the Wronskian equals e to the 2t. And then I was like, that's all the pieces you need. All right, identify the Wronskian, identify y1, y2. Let's plug it into the variation of parameter formula for the particular function. All right, and I'm just going to keep writing the particular. Just keep practicing, keep trying to commit this to long-term memory.
Does it ever matter which function gets negative?
The negative y1. Now, does it matter if you pick y1 or y2? No, because if I switched the order of these, right, then this probably would end up negative. The Wronskian would end up negative. All right. But as long as you're consistent, as soon as you pick y1 and y2, then yes, the equation it's negative y1, positive y2, because actually this can expand, all right, to y3, y4, etc., and it goes back and forth, negative, positive.
It's not like integration by parts where there's like a flow chart of like obviously better variables to pick for v, better variables to pick for u.
Correct.
That doesn't exist here.
No, that does not exist. That does not exist at all. Yeah.
Okay.
Like, yes, which one integrates better and which one differentiates better? Yeah, no.
Okay.
I was like, but the formula has this is
Yes,
negative and now it's positive. Yes. some algebra, leave it, change the flip and stuff.
Wait.
That's over one, that's over one. Hold up. That goes away, this becomes t all over t squared plus one dt plus t e to the t. That goes away, this becomes one all over t squared plus one dt. So, again, actually simplifies pretty nicely. So, for the left one, what do we need to do? U sub, this is U sub all the way. Beautiful U sub.
What about you?
Go ahead.
I said beautiful.
It is. All right. What about the right side?
Our method? Like t to the negative, I guess you really can't do that, right? Like t squared plus one to the
Oh,
negative.
reverse power rules. which
Yeah,
is-
sorry about that.
No, not with that guy. Do we have our integration charts?
I know, is there a special try, is there a special one for that?
It's gonna be an inverse.
Oh, well done. Inverse what?
Arctan?
It is arctan.
One over a, arctan,
Yeah, 1 over a squared plus 1 over x squared, which
Yeah.
means that what's a?
one.
1. Oh, look, it's just straight arctan. Yeah. Oh, good job. I was like, this is by far the most common one, and the temptation is to try and do a U sub or try and do LN or try and do junk, right? It's just that's inverse tangent. Well done. Okay. Plus t e to the t. And is this just tan inverse of t? I was like, there's nothing else to be done on that one. Yeah. So this becomes u, and that actually then just becomes ln, right? So negative 1/2 e to the t. So that's ln of that whole thing, t squared plus 1 plus t e to the t arctan. Yeah, that is the particular. That actually simplified out pretty nicely. So the general solution.
Got 10 minutes.
Okay. Just trying to think. Yeah, let's write this up. Once again, I was like, notice this follows the same principles that we had with undetermined coefficients. The constants, right? They all have constants. Does each one link to a distinct function?
Yes.
Yeah, right? Distinct function, constant 1, distinct function, constant -1/2, C1, C2, right? So each one has a distinct function associated, right? But once again, just when we look through these, we notice these are definitely not the same as those easy ones we were doing in undetermined coefficients. All right, you guys want to finish this off or wait till next time? Don't watch. But it's up to you. I'll leave this one to you guys since that's the time.
Yeah, it doesn't matter.
Doesn't matter?
I mean,
Okay, if I get to choose, then we'll finish. Oh. All right, so find the general solution to the differential equation. Notice this one actually presented, all right? y1 e to t, y2 t plus 1 is a fundamental set of solutions. So we were given y1 and y2, so we can create the complementary solution. And then in order to do variation of parameters, I have to make sure I'm in the correct form. Form is everything. Second derivative needs to be a coefficient of 1, so let's divide by t. And the big thing that actually changes, right, is it changes g of t. Because g of t we're going to use in our equation. Once I have that, I have y1 and y2 identified already, which means we can identify the Wronskian and proceed to variation of parameters. But form, right, we've said it from the beginning, form is everything. Need to make sure that when we write our equations, we have them in the proper form. Especially because we're using a formula that's based on a particular form. Which gives us negative t e to the t for the Wronskian, and we should be able to then set up our formula for variation of parameters negative. Well, it was e to the t. Right, and g of t is simply just t here, right? I haven't been explicitly identifying this because it's whatever is on the right side, right? And this is why the form is important, because if you plugged in this one, I would end up with t squared, it'd be all messed up, which is why we have to make sure form is correct. So g of t is just t. T e to t. Negative t e to t dt. All right, let's simplify this down. Negative that goes positive out there. E to t. All right, t and that one cancels. So now it's gotta get some t plus 1 all over e to t. Actually, this becomes a negative because of that negative. The t's cancel. Oh, t's canceled. It's like my favorite integral ever. Okay, so that one's obviously easy. What do we need to do here?
By parts.
It's by parts, right? This guy comes up. Because this becomes t plus 1, e to the negative t dt. This is by parts. It's integration by parts all the way. Okay, that one actually simplifies enough. I was like thrown off because it just all goes away apparently. Okay, so ends up just being negative e to the negative t.
Negative T to the T.
Jesus. I was like, I couldn't find where it was the zero t e to the negative t minus e to the negative t. Okay. That is hopefully what that should become. The other piece then is t plus 1 times t. Okay, so that by parts results in that. Then, all right, what do we multiply through? Then that becomes negative t minus 1 minus t squared, rainbow that through, minus t. This whole thing that should then simplify down to negative t squared minus 2t minus 1.
When I did the integration by parts, I got it to just be negative T, e to the T, e to the negative T, excuse me.
When you did you do the integration by parts?
Mhm.
Okay, I shouldn't be. What did it result in?
Negative T, e to the negative T, because
So it is just that.
yeah, it's just that. Because I'll do it again. I mean, I very well could have.
I was like, trying to skip steps, and I was like, nice. I was like, I was like, gonna need to do this all minute. Because I was trying to be fast. T, which just gives us. Okay. Just have to back up. But this is. So t plus 1 negative t minus, which becomes plus e to the negative t dt.
No, I messed it up.
It's okay. You're not the only one today. It's like e negative t. Negative e to the negative t. Integrate that becomes minus e to the negative t. Negative t e to the negative t minus 2 e to the negative 2.
Yeah, that's what I got on the second time, yeah.
Okay. All right. Back to where we were. Okay, so then that thing multiplied by e to the t. So back to our y of p. So e to the t times negative t e to the negative t minus 2 e to the negative t. All right, the other piece minus t plus 1 times, and then integrated constant just becomes t. All right, so almost done. Okay, now bring that through. That becomes negative t. That goes away, minus 2 minus t squared minus t. Okay. So we end up with negative t squared minus 2t minus 2. All right. Finally. Y of t is then c1 e to the t plus c2 t plus 1 minus t squared minus 2t minus 2. All right. And once again, Actually, this kind of looks like all that we could have done. I was like with undetermined coefficients. But I was like, all the coefficients are solved. That is the real benefit of variation on parameters. Right? It solves the constants instead of doing a bunch of algebra to solve that afterwards. All right, we will pick this up 1 week from today. Next class, we have an exciting
Pretty much.